Hello, today we'll discuss Thevenin's theorem. Current flowing through a resistor, if there is a resistor in the circuit which is connected across any two terminals, suppose A and B, of any active network, then the current flowing through that resistor is obtained by dividing the potential difference between A and B with R is disconnected. Okay, where R is disconnected by some internal resistance plus the total resistance of the circuit, where R is the resistance of the network which is measured from the terminals A and B. Okay, so the statement of this theorem is like that: an active network having two terminals A and B can be replaced by a constant voltage source can be replaced by the constant voltage source having an EMF capital E and an internal resistance, suppose small r, internal resistance small r. Therefore, the value of E is equal to the value of E is equal to the is equal to the open circuit potential difference between A and B, and R is the resistance of the of the network measured between A and B with load resistance with the load disconnected and sources of EMF replaced by their internal resistance. Okay, so this is the statement of the Thevenin's theorem. So if there is active networks having two terminals A and B, which can be replaced by the constant voltage source having an EMF P and an internal resistance R, therefore the value of E is equal to the open circuit potential difference between A and B, and R is the resistance of the network measured between A and B. With load disconnected and sources of EMF are replaced by their internal resistance. So this is the statement. Now according to the statement, we'll draw the circuit diagram. There is a any network which is having the terminals like this. This is a network. This is having EMF E. There is one resistance is there. There is one more resistance is there. This is the resistance, and this is the terminal A and B. This is E1 and this is a R1, this is R2 and this is R3, and this is your load resistance. We can call it as R. Okay, so according to the statement, we have to find the current flowing through this resistance, and this can be found by using the Thevenin's theorem. So we have seen that we have to replace, we have to open circuit, we have to disconnect this. If you disconnect this, your circuit will become like this. According to the statement of Thevenin's theorem, we have to disconnect the load, and if you disconnect, this will become open circuit, terminal A and B. So this is E1, this is R1, this is R2 and R3. And now we have to measure the internal resistance, and this internal resistance can be measured from this open circuited terminals A and B, whereas this EMF source we have to also replace by their internal resistance, if any, if there is any internal resistance. So according to the statement, R is the resistance of the network measured between A and B, with load disconnect and sources of EMF replaced by their internal resistance. So according to this, we have to find the internal resistance, and we have to replace the internal resistance by their. So there is no internal resistance, we have to just replace by its short. So this is a R1, this is a R2, this is R2, and this is your terminals A and B. Okay, this is a R3 and this is a R1. Okay, so here we have to find the total resistance. Now the current flowing through this, we have to calculate. Current through R3. What is the current flowing through the R3? This current we have to calculate. The current flowing through the R3 is this. We will call this current as a I1. We'll call this current as a I1. Therefore, the current flowing through R3 is equal to, how can calculate this current flowing through R3 is nothing but this voltage upon this resistance. So voltage is here E1 and resistance is R1 plus R3. Okay, so this is the current flowing through the R3. Now what is the potential difference across R3? It is nothing but the current through the R3 into the resistance. So what is the current through the R3? It is a E1 by R1 plus R3 into, what is the current? Current is this, and resistance is this. So this is the potential difference across resistance. So E1 into R3 divided by R1 plus R. Since there is no current in R2, there is no current flowing through the R2 because it is open circuited. Only the current is flowing through this loop, and there is no current flowing through the R3 because it is open circuited. Okay, therefore no current is flowing through the R2. Therefore, potential difference across AB is nothing but the potential difference across this R3. The potential difference across AB is equal to, we'll call that as a V. Therefore, no current is flowing through this. Therefore, the potential difference across AB is, we'll consider this as a V. Therefore, voltage V is nothing but same E1 into R3 by R1 plus R3 if you view from the open circuit terminal. So therefore, shows the network with the load disconnected and the battery is replaced by the internal resistance. So this is the last circuit. Load is removed and battery is replaced by its internal resistance. As there is no internal resistance, it is circuit will be like this. Here we have to find the internal resistance of the circuit, as these two are connected in parallel and the parallel combination of the circuit is connected in series with the R2. Therefore, we can find here that internal resistance which is viewed from the open circuit terminal is nothing but this R2 plus R3 into R1 by R3 plus R1. So this is the internal resistance we have to view from the circuit. Now, according to the Thevenin's theorem, we can now write, we have the EMF E1 and this is the internal resistance we have find. This is R and this is the load resistance R and this is a terminal A and B, and we have to find the current flowing through this R which is same, and the current flowing through R, current through R is equal to I, and which is equal to this E1 by R plus capital R. So this R is this internal resistance of the circuit which is viewed from the open circuit terminal, and this R is the load resistance. So in this way we have to develop the Thevenin's network. This is called as the Thevenin's equivalent circuit. So whenever any circuit is given and it is asked to find the current flowing through the load resistance by using the Thevenin's theorem, we have to find first the Thevenin's equivalent circuit. Okay. Let us consider one example. We have the circuit like this, having the two EMF sources, and there is a resistance, and this is actually the load resistance, and this load resistance, it is given, it is a 10 ohm. This is R1, this is R2, this is a 2 ohm R1, R2 is 3 ohm, and these sources are given. This is E1 is equal to 6 volt, and this is E2 is equal to, this is 4 volt, and this is the C and D terminals of an active network, and we have to calculate the current flowing through this load resistance R3 by using the Thevenin's theorem. Okay, so according to the definition of the Thevenin's theorem, what we have to do? We have to just replace this load resistance. When you replace this, your circuit will become like this. This is C and D. Now this is open, and this is E1. This is E2. E1 is here. It is given 6 volt. This is the 4 volt, and this is a 2 ohm, and this is 3 ohm. Now what we have to do? We have to find the current flowing through this branch, this loop. The current flowing through this loop is suppose I1, and this can be found by applying the KVL. We have to apply the KVL. Apply KVL to loop. So you are going in this direction. So it is a 6 volt from negative to positive. And again we are coming here. So there is a positive to negative. Here it is a from negative to positive. There is rise in voltage. And here from it is a positive negative. There is a fall in voltage. Again come here. There is a fall in voltage. So it is minus 3 I1. And again there is a fall in voltage. Therefore 2 I1. And this is equal to 0. Therefore we can write here 6 minus 4 2. This is a 5 I1 is equal to 0. And what we get here? Minus 5 I1 is equal to minus 2. Therefore I1 is equal to 2 by 5, and this is equal to 0.4 ampere. This is equal to 0.4 ampere. Now we have got the current flowing through this. Okay, and what is the potential difference across this terminal? We have to find the potential difference across this terminal. So therefore the potential difference across CD is potential difference across CD is, it is a EMF source is there. This EMF, this is same. The potential difference across CD, as these two are connected across the CD, therefore we can find a potential difference across this branch or this branch, one and the same thing. Therefore potential difference across CD is E1 minus 2 into I1. This is a resistance. Okay, it is a, this will be current 2 into I1. Okay, so this is nothing but E1 is here 6 volt minus 2 into I1. We have got here 0.4, and this is coming equal to 5.2 volt. So this is the value of E1. Okay, therefore we have got E1. Now we have to find the total resistance from this open circuit, or we can say it is internal resistance. So for that we have to replace this EMF source by the internal resistance. There is no internal resistance mentioned here. Therefore we have to just replace it by the short line. Okay. So for measuring the internal resistance of the circuit, so we have to replace EMF source by the short line, and this is the we have to view from this terminal, and this is 2 ohm and this is a 3 ohm. Therefore the resistance here R, that is internal resistance viewed from this terminal, 2 into 3 by 2 plus 3 is equal to 6 by 5, and this is equal to 1.2 ohm. This is internal resistance. Now we have got internal resistance, we have got also this E. Therefore we can write here equivalent, Thevenin's equivalent circuit. Thevenin's equivalent circuit is like this. This is the E, this is the internal resistance, and this is your load resistance. So E we have just calculated. We have got E is equal to 5.2 volt. Potential difference across CD is E.